Hey everyone, so we are at topic 11, which is on Bootstrap and Jackknife methods. And personally, this is one of my favorite topics in the whole course. Yeah. So before we begin, let me take a few moments to really see what we are going to cover. So first is we are going to talk about what do you understand by, what does it mean by resampling methods. And then we will first talk about the non-parametric bootstrap, okay? And then we will cover the Jackknife, which is the older version, and it is simpler. And we will do the bootstrap on the confidence interval, and note that there will be 5 different types of these methods, and then you need to understand the pro and cons and what are the trade-off among them. And then we will also look at the Jackknife after bootstrap diagnostic, and then we're going to wrap up with some cross-validation and some philosophies around the resampling methods. Okay. So if we want to talk about the resampling, first is I want you to understand what does it mean. Okay. So let's take a step back and then let's revisit of what you have learned in the previous statistical course. So you may learn something like this, yeah. So assume that the data come from a normal distribution, and then we can derive some exact formula for the confidence interval and hypothesis testings. And we also learn about the central limit theorem, which says that the sample means can be approximately close to, or it can be approximate by normal distribution when we have a large sample, regardless of the shape of the population. So these are very powerful. But the problem is, what happens when you don't know the population distribution? Okay, so what happens when you estimate something more complicated? Okay, for example, if you want to estimate the ratio or the correlation or the quantile or some regression coefficient which come from nonlinear model, okay, or some other complex function. So in many of these situations, the sampling distribution can be very difficult to solve. Okay, so we cannot write down this estimation in a closed form formula. Well, the central limit theorem might be useful asymptotically. This is the case for the very large sample, but for small sample, it can give a very poor approximation. So that is why we need to have these resampling methods. Okay, so instead of relying on the mathematical derivations, which is based on the assumed population models, we can use the resampling methods on the data itself as the basis of reference. Okay, so this is a very simple, but it is also very, very powerful. So now let's talk about the core problem of the inference. Yeah. So the first is the traditional inference relies on the assumptions of a population distribution F. So this is the key starting point. Yeah. So when we set up a statistical model, we usually postulate that the observed data may come from some family of distribution. For example, we might assume that X follows a normal distribution with some unknown mean and variance of the sigma squared. Or we might assume that the count data follow a Poisson distribution. So all of this classical machinery, like maximum likelihood estimation, like t-test, chi-squared test, and f-test, all this is built on these kinds of distributional assumptions. So if the assumptions is correct, then this method will work. Yeah, but if the assumption is wrong, then the method can give very misleading results. So often F is unknown, and the statistic of the data set has a sampling distribution that is mathematically intractable. So this is really the main problem. Yeah, this is really the center of the problem. So in reality, it is very rare that we know with certainty that our data come from, for example, come from normal distribution. So we can check for the goodness of it, but we can never be sure. Okay, and even if we accept a model, the sampling distributions for complicated statistics, for example, like you are interested in estimating the ratio between, or the ratio of the two sample means. Okay, so in this case, this ratio may not have a clean form or a simple form. So to derive it, it will require like a very, very long calculation. Okay. And then the traditional methods such as the central limit theorem are asymptotic, okay, which means that they may not perform well for a small sample size. So even when we apply the central limit theorem and it tells us that the statistic is approximately normal, okay, but this is just an approximation. For small sample, for example, like n is equal to 10 or 20, then in this case, the normal approximations for the sample distribution might be quite poor, especially if the population is skewed or the population is heavily tailed. So, the main problem with this is that we want to make inferences about some population, quantity, data using our data, okay? But then we cannot easily characterize the sampling distributions of our estimator data set. And therefore, we want to consider how we can use the resampling methods to provide the solutions to this problem. Now, let us first talk about the resampling paradigm. Okay. So, the resampling method treats the observed sample as a finite population. So, instead of asking what would happen if I draw many samples from the true population, let's say the population is F distributed, okay, so what will happen if I draw many samples from the true population F, which I do not know? So the resampling method will ask the questions of what will happen if I draw many samples from my observed data sets, which we already have, okay. So in this case, we use the observed data as a proxy for the unknown population. Okay, so in a sense, we can say that we are pulling ourselves up by our bootstrap, which is literally where the name of the bootstrap come from. Okay, so we generate the random sample from this pseudo population to estimate the population characteristics. So we generate many replicated samples from the same amount of our observed data, and then from here we build up the empirical picture of the sampling distribution or the statistic that we target, for example like the standard error, bias, confidence interval, and then we let the computer to do the work that we don't have to solve them analytically. Okay, so there are two primary methods. The first one is the bootstrap, which is a non-parametric Monte Carlo methods based on the sampling with replacement from the observed data. And the second is the Jackknife. So this is a more systematic and it is also more deterministic methods based on the leaving out one observation at a time. So both of these methods will be covered today. Yeah. Okay, so just one thing before we move on. I would like to say that these methods are powerful, yeah, but they have some assumptions and limitations of their own. So it is also very important for you to know or to look at these assumptions and the limitations. Now let's go to the non-parametric bootstrap. Okay. First is we are going to talk about this empirical distribution function, or the ECDF. Okay, so this is the mathematical foundations of the bootstrap. So let us explain about this one. So the ECDF, which is denoted by the F sub n of x, is defined by the formula given in here. Okay. So let's say we have a sample of n observations. We have x1, x2, all the way to xn. So the ECDF of any value of x is equal to 1 over n times the sum of I equal to n of this indicator function of xi less than or equal to x. So basically what this means is this fn of x is the proportions of sample observations that are less than or equal to x. Okay. So why is this important? So first is fn of x is a sufficient statistic for f of x. So in statistical theory, a sufficient statistic contains all the information in the data about the unknown parameter. So in this case, it means that the ECDF, which is just the observed empirical distribution of the data that we have in our hands, is the best non-parametric estimator of the true and unknown population of the CDF of F. Okay. So the second point is that it is the distribution function of a random variable that is uniformly distributed on the observed sets of X. So this is a crucial point of the Bootstrap. Yeah. So the ECDF is the distribution that assigns equal probability, which is 1 over n, to each of the observed data points. So let's say if we draw a random sample from the distributions of Fn, so we are doing we are doing this thing. So we randomly pick observations from our original data sets, and each have a probability of 1 over n. And since we are sampling a distribution, okay, and we are sampling a limited distribution, which is not a finite list, so we have to sample with replacement. So this means that we pick the same observation more than once for each of the Bootstrap sample. So the ECDF will give us a way to formalize what treating the sample as a population means. So it means that using the Fn instead of using F. Now let's talk about the Bootstrap concept. Okay. So in the ideal inference, we like to go from the population distribution F to our estimated data head. And then we need to understand the full sampling distributions of the data head. But we do not have F. Okay, we do not have F. We only have our observed sample X. So this is the first approximations that we do. So if we look at the first approximation here, okay, so the population F goes to observed sample X. So we replace the unknown F with Fn. Okay, which is the empirical distributions of the observed data. So the approximation 2 is when the observed sample X goes to the Bootstrap sample X star. And once we have replaced F with Fn, and then we can simulate the new sample from Fn, which is by drawing the samples with replacement from our observed data. So these simulated samples are called the Bootstrap samples. And then we denote them as X star. Okay. So resampling from the sample is equivalent to generating random samples from the distributions of Fn of X. So this is the mathematical justifications for what might seem like a strange trick. So we are not just doing the resampling, we are genuinely simulating from the estimated population distribution. Okay. So in other words, let's think of it this way. Suppose that we are trying to understand the variability of some statistics. Okay, let's say this statistic is a data head. So in the real world, you like to repeat the entire experiments many times. So you draw a new sample from F, and then you compute the data head, and then you repeat. But in reality, we cannot do this. Okay, so we only have like one set of data. So this method, this Bootstrap method, it says that pretend that your data set is the population, and then you resample from it. And then for each of the sample, you compute the data head on each of the resample data, and the variability of the data head across the Bootstrap, okay, will tell you about the variability of the data head in the real world. Okay, so even though this is an approximation, but the practice or so far shows that this is a good one. Now, what is the algorithm of this Bootstrap? So the goal is to estimate the sampling distributions of a certain statistic data head. Okay, so the first step is for each of the replicate B, So we have from 1 to capital B, and B is the number of bootstrap replicates that we want. Okay. So what we do is that we do two things. The first one is that we generate a bootstrap sample x star of B. Okay, so this is written as a set of x star 1 until x star n. And then this is sampled by replacement from our original sample x1 until xn. And note that this bootstrap sample has the same size as the original sample. And because we are sampling with replacement, so some of the original observation will appear multiple times in the bootstrap sample, and others will not appear at all. Okay, so and on average, we can say that there are certain percentages of the original observations which will appear at least once in a given bootstrap sample. Okay, so we will talk about this later on, especially when we go to the Jackknife after bootstrap. So and then we for each of the bootstrap, we compute the replicate theta hat of B, okay, which equals to the theta hat which is evaluated on the x star of B. Okay, so in this case, we apply our estimation procedure to the bootstrap sample, which is exactly as we apply it to the original data. And then the second step is when we use the empirical distributions of the theta hat 1, theta hat 2, all the way to theta hat B. And then we use this to approximate the sampling distributions of the theta hat. And this is what it means by the bootstrap approximations to the sampling distribution. And from these empirical distributions, we can compute the bootstrap estimates of the standard error, and then we can compute the bias and confidence interval, all of which we'll cover in the following slides. Okay. So the bootstrap, I also want you to understand that the bootstrap is a Monte Carlo method. Yeah. So in this case, you don't need to do any of the mathematics or calculus. You just need to be able to write a function that can compute a statistic on the data sets, and then you run it on the B bootstrap samples. Okay, so the computer does all the work without the analytical solution. Now let's look at this one. Okay, I would say that the bootstrap estimations of the standard error is the most common applications of the bootstrap. Yeah. So it is given by this formula. So we have the estimated standard error of the theta hat star. Okay. So this formula is exactly the same as the sample standard deviation formula, but this is we just adopt it into the case of the bootstrap replicates instead of using the original data. But if you can see, this is actually very familiar. Okay. So think of it from the first principle. Okay, so the standard error of the theta hat is the standard deviations of the sampling distributions of the theta hat. So okay, and the bootstrap sampling distribution, which is the empirical distributions of our bootstrap replicates, is the approximations of the true sampling distribution. So in this case, the standard deviations of the bootstrap, which is replicate, will approximately the true standard error. Okay, so from here we can estimate the standard error of any statistics. Okay, it doesn't matter how complicated it is. We can just estimate the standard error just by computing the statistics on the many bootstrap samples and taking the standard deviation. Now let's talk about the estimations of bias. Okay, so this is also an important application of the bootstrap. So as you can see here in this equation, it shows that the bias of an estimator theta hat is defined to be the expected value of the theta hat minus the theta, which is the average amount by which the estimator deviates from the true parameter value. So if the bias is positive, our estimator tends to overestimate the data. If it is negative, then it tends to underestimate the data. Okay. So the absolute value of the bias divided by the standard error is less than or equal to 0.25, and the bias correction is usually unnecessary. So this is This is like a guidelines. Yeah. So if the bias is small relative to standard error, which is less than 1/4 of the standard error, then if we correct for this, it will only slightly change our estimates, and it may not be worth the additional complexity. But if the bias is larger than this, and then maybe we should consider a bias corrected estimator. Okay. Now let's look at how this is applied in the case of correlation standard error. So in this case, we want to compute the Bootstrap standard error of a correlation coefficient. Okay. So first is we need to use the boot package in order for us to run the Bootstrap calculation. And then starting from, we are going to use the data, law data, okay, which is from the package Bootstrap stuff. Try to run this R code. Yeah. I think this data sets contains the LSAT scores, yeah, and the undergrad GPAs, and it contains the observations of 15 law schools. So it is a very, very small data set. So what we want to do is we want to estimate the correlation between the LSAT and also the GPA. So LSAT is some scores, yeah, some academic scores probably, and then we want to see the correlation between the two. So our data here is the correlation, and we also want to assess how variable that estimate is. Yeah. So we use a function of score stat here, in which this is a function of two parameters. The first one is we have dat, which is the data frame indices, which is a vector that should contains the Bootstrap sample, and inside the functions we compute the Pearson correlation between the two variables. Yeah. And then we do these samples. Okay. Let me see. Okay, and then we run the Bootstrap using the boot function, where data is equal to law and the statistic is based on the core stats that we compute here, and then we run the replications for 2000 times. I think somewhere in the boot functions, because we didn't really specify the sampling with replacement, but it is assumed, you know, by default that it will run the sample with replacement. Okay. So take some time to run this code yourself, and then you can try to change the replications number using various number. You can put like 10 or 50, and then you can go up to 2000, 10,000 and all that, and see what you find. Okay. So the next question is, we want to ask about the practical question. Okay, how many replicates of B do we need? So how many Bootstrap replicates do we need? And this is the questions that we always ask. Okay, and the answers is depend on what we are computing. So in the case for the standard error estimation, usually B equal to 50 is often enough, and when B is equal to 200, this is considered as plenty. This is because the standard error is just a standard deviation from the Bootstrap distribution, and it usually for the standard error estimation, it stabilizes quickly. Okay, even with only 50 replicates, you can get a good estimate of the standard error. So number 2 is for the bias estimation. So the bias estimation will need a higher number, so generally between 400 to 2000. So the bias is the mean of the Bootstrap distribution minus the original estimate. Yeah, which means that it will stabilize more slowly than standard deviation, especially when the distribution is skewed. So in this case, we need more replicates to get a stable estimate. And then we have confidence interval. So in this case, we need to have B at least 1000, and if you have a more sophisticated interval, maybe, for example, like you have a BCA interval, and then you will probably need 2000 or even more. Okay, so why? Because confidence interval depends on the tail of the Bootstrap distribution. And when it involves the tail, this is the part that require the most replicates to characterize the accuracy. Okay, so because of the computing power in the modern computing, running a 2000 bootstrap replicates for a simple statistic such as correlation will only take a fraction of the second. Okay, even for complex statistics, it may take a few seconds or a few minutes, but the competition is cheap. So if you're not sure, you can always increase the number of B. Okay, so usually when B is equal to 2000, this is considered as a safe for most of the application. Now let us talk about the Jackknife. Yeah. So the Jackknife is actually older than the Bootstrap. I think it was developed by in before 1950s. Yeah, and then it was further developed by John Tukey in somewhere in the 1950s. So the name Jackknife comes from John Tukey himself, I think, who were inspired by a pocket knife, which is, as I said, it is a simple and a general purpose tool. Okay, so what is the core idea of the Jackknife methods? So the Jackknife was developed earlier than the Bootstrap by I don't know how to pronounce it, Connoir in 1949. So it is important to understand that the Jackknife was actually introduced before the Bootstrap by many years. Yeah, and the Jackknife is a leave one out resampling plan. So this is the defining characteristics. So if the Bootstrap use sample with replacement, the Jackknife, what it does is it systematically remove one observation at a time. And then the ith replicate is given by the data head of I. Okay, and this is given by the data head of X minus this one particular observations. Okay, so for the Jackknife estimates of bias, for smooth plugin statistics, the Jackknife estimate of the bias is given by n-1 times the data head of the data head dot minus the data head. Okay, so this data head dot is the average of all the leave one out replicates, and then the bias estimate is n-1 times the difference between this average and the original estimate of the real data head here. Okay, so I want you to understand why we need to multiply with n-1. So this is what we call as the correction factor. Okay, and this is what makes the Jackknife bias to work properly. So to understand where it comes from, let's think about the bias of the for example, like the maximum likelihood estimate of the variance. Yeah, so let's say if you have n observations, and this is from normal distribution, and then the MLE of the sigma squared is 1 over n times the sum of squared of the deviation from the mean. But this is considered as the bias estimator because the true variance of the sampling distribution is actually sigma squared, but the MLE will estimate it as n-1 over n, and this will multiply with the sigma squared on average. So the factor of n-1 alone, this is in the Jackknife bias formula, is designed to correct for this kind of bias. Yeah, so okay, so next is the Jackknife estimates of the standard error. So the formula is given by the standard error head of the Jackknife, which is given by this formula. And as you can see here, we still have like the data head I minus the data head of naught. In this one is the the leave one out sample, and we take the square root and then we multiply with n-1 divided by n, and then we take the square root of it to get the standard deviation as the standard error. Okay, so so the factor of n minus 1 divided by n, and okay, this makes the estimated standard error becomes the unbiased estimator for the standard error of the sample mean. Yeah, so in other words, for the sample mean, the Jackknife standard error will reduce exactly to the classical standard error formula, which is the square root of the sample variance divided by m. So basically what happened here is that the Jackknife reproduced the classical results for the sample mean. And the second bullet says that unlike the Bootstrap, the Jackknife is deterministic, no random sampling involved. Yeah. So in this case, given a data set, the Jackknife will always give you exactly the same answer, which means that there is no Monte Carlo variability in the Jackknife estimate. So you don't have to worry about running it for multiple times, or you don't have to worry about choosing a number of replicates. You just have to run it once and then you get the answer. Okay, so this will make it computationally efficient to get the smooth statistics, because it requires exactly the number of n evaluations of your statistics. Now let's talk about when the Jackknife will fail. So the Jackknife works well for smooth statistics, for example, for means, variance, and correlation. Okay, so the keyword here is smooth statistics. So what does it mean by smooth statistics? So the smooth statistic is one that changes continuously and gradually as the data change. So let's say if you change one observation by a very, very small amount, so the smooth statistic will change correspondingly small. So for smooth statistic, if you leave one observation at a time, it will give you a good sense of how much the statistic varies across the different samples. And then the second point says that it fails for non-smooth statistic like the median. So a median is a classic example of a non-smooth statistics. Yeah. So let's say we have a data set of an odd size. Let's say the size is n, and the median is the middle value when the data is sorted from the lowest to the highest. So if we leave one observation out, okay, sometimes the median can jump by quite a substantial amount. Yeah. So it can jump from one value to a completely different value. So this is what it means by the non-smoothness. And then the small changes in the data set, which is leaving one out, can lead to jumpy changes in the median, which lead to inconsistent standard error estimates. So the Jackknife assume that the variation across the number of replicates will accurately reflect the true variability of the statistics. But on the other hand, the non-smooth statistics, so this assumption will break down, and then what happen is the Jackknife standard error estimate can be either too large or too small, or it can be inconsistent as the number of sample grows. Yeah. So the key takeaway here is for non-smooth statistics like the median, the quantile, and the maximum, you should use the Bootstrap instead of the Jackknife, because the Bootstrap will handle the non-smooth statistic much better, because it explores the full empirical distribution rather than just the n leave one out perturbations. Now let's look at the example, and in this case we use the Jackknife for ratio estimates. Yeah, and for this one we will be using the patch datasets from the package Bootstrap. So I want you to take some time. You can pause this video. You have to run this in our code, yeah, or in our script, and then see the answers. So the patch dataset, it contains the measurements y and z for n number of subjects, and then we want to estimate the ratio of the data head equals the mean of y divided by the mean of z. So the ratio statistic here is the mean of y divided by the mean of z. And this is considered as a smooth statistics, so it is appropriate to use the Jackknife. So first is we define n to be the number of row of the patch data sets, and then y and z we extract it and then we put it as y and z, and after that the data head is given by the ratio statistics, which is the mean of y divided by the mean of z. And then we do the Jackknife replicates. So we have the data jack, which is an empty vector of length of n, and then we run the looping function for I in 1 to n, and then we record the data jack, which is given by the ratio statistics. And for each of these ratio statistics, we put the negative sign here so that this is a leave one out observation. So in the first loop, it will leave the first observation, and then in the second loop, it will leave the second observation, and so on. Okay. And then after that, we compute the bias and we also compute the standard error. So the bias and the standard error is following the formula that was shown in the previous slides. Yeah, and then you can find that you can find a certain value of this bias and also of this SE. So try to run this code and then let us discuss what does this bias and standard error means. Yeah. And you can compare this to the Bootstrap. Okay, so let's say you rerun this and then using the Bootstrap, and then you can run it for B number of times and then try to compare to the results of the Bootstrap. Now let's go to the next subtopic, which is on the Bootstrap confidence interval. Okay, so this is one of the most practically important topic in the whole lecture, and I really want to spend some time on this one. Yeah. So there are 5 major methods to construct the Bootstrap confidence interval, okay, and they would differ in their assumptions and also in terms of the computational complexity and also their statistical properties. Yeah, so let's look at all the 5 methods to construct the 100 times 1 minus alpha percent intervals. So the first method is the standard normal interval. I think we are all very familiar with this. Yeah. So this is the simplest method. We assume that the data head is approximately normal distributed. And the second one is the basic Bootstrap interval. So this method will use the quantile of the Bootstrap distribution, which is the data head star minus the data head, to construct the interval. Number 3 is the percentile interval. So this method will use the quantiles of the Bootstrap distribution of the data head star. And then number 4 is the Bootstrap T interval. So this is using the classical T interval, but then we use the Bootstrap estimated standard error. And this one will require a nested Bootstrap, which we will talk about later. And the last one is the BCA, or bias corrected and accelerated. So this is the most sophisticated method, and it is considered as the gold standard. Yeah. So let's go through each one of these in more detail. But whenever we talk about this, I want you to think about the trade-off, yeah, between the complexity and also the accuracy, between the computational cost and versus the reliability. So these are the trade-off that you should think of whenever you choose which one you want to use. Yeah. So now let's start with the standard normal interval. So it is given by the data head plus minus some z value of the alpha divided by 2 times the estimated standard error of data head. Yeah. So this one is, I believe that for all of you, this look very, very familiar. Yeah. So this is exactly the classical confidence. This is the classical confidence interval formula. So the only difference is that we use the Bootstrap estimate of the standard error, which is the SE head here, okay, and then which is computed from the Bootstrap replicate that we described before this, okay. So this is quite simple to compute, and it requires the sampling distributions of the data head to be approximately normal and unbiased. So this is basically the central assumptions lah. So if data head is not normally distributed, for example, if the distribution is heavily skewed, and then this interval will not have the correct coverage probability. Yeah. And then when we talk about the bias, if the data head is biased, and then the interval will be centered in the wrong place, and then the coverage will be poor. Okay, so the standard normal interval is the simplest Bootstrap confidence interval to compute, but it is also the least reliable for, especially for non-normal or some bias estimator. Okay, so it can capture some key advantage of the Bootstrap, where we use the Bootstrap standard error. So we do not need to have the mathematical formula for SE, but it may also throw away some information about the shape of the Bootstrap distribution. Okay. So the second one is the Bootstrap, the basic Bootstrap interval. So the interval is given by 2 times the data head minus the data head star of 1 over alpha divided by 2 until 2 times 2 times data minus the data head of alpha divided by 2. So the key idea here is to use the quantile of the sampling distribution, of the data head minus data to construct the confidence interval. So use the quantiles of data head star minus the data head. And we do not know about the distributions of this data head minus data, but we can approximate this with the distributions of data head star minus data head. Okay, so this data head star is the Bootstrap replicates, and the data head is play the role of the data in the Bootstrap world. Okay, all right. So the basic interval does not have to assume normality, but it does assume that the distributions of this data head star minus data head would be a good approximation to the distributions of the data head minus data. Okay, so when the distribution is skewed, or when there is a bias, and then it can perform quite poorly. So the next one is the percentile intervals, which is probably the most intuitive of the Bootstrap confidence interval. So this is given by the data head star of alpha divided by 2 and the data head star of 1 minus alpha divided by 2. Okay, so so for like example, like when alpha is 0.05, for 95% interval, so we take the 2.5, 2.5 and 97.5 percentile of the Bootstrap distribution. It is as simple as that. So what is the advantage of this percentile interval? It is intuitive. So if 95% of the resample statistics falls between L and U, where L and U is the interval, so if the Bootstrap distributions of the data head star is concentrated between L and U, and then we are confident that the data should lie in this range. And then it is transformation respecting, which means that if L and U is a percentile Bootstrap confidence interval for the data, and then the GL and GU is a percentile Bootstrap confidence interval for the G of the data for any monotone transformation of G. So this is very good, because for example, if you bootstrap the log of the standard deviation and then you exponentiate the interval endpoints, so you're gonna end up with having a valid confidence interval for the standard deviation itself. So the classical intervals based on the normal approximation may not have this property. But despite its intuitive advantage here, the percentile interval can have a poor coverage when the Bootstrap distribution is biased or skewed. So you can see that all of this, when we have standard normal interval, basic Bootstrap interval, and percentile interval, all this will perform poorly if we have a distribution which is biased, or having a heavy skewness. Now let's talk about the next one, which is the Bootstrap T, which is a studentized T interval. So the algorithm of this is, the first step is we compute the data head and the standard error of the data head from the original data. So that's why we have the estimated standard error here. Okay. And the second step will be for each of the bootstrap sample B, we compute the T statistics, which is the T of B, okay, given by this formula. And then the step number 3 is, okay, so this is where the complication happen. Yeah. So this standard error or estimated standard error of the data head star of B must be estimated for each of the bootstrap sample, which would require to have a nested bootstrap. Okay, which is for each of the B outer bootstrap sample, you run another inner bootstrap of another, let's say another replicates. Let's say the outer bootstrap sample or the outer replication is B, so the inner replication is B2. Okay, and then the fourth step would be using the quantiles of the resulting B values of a T and B, T of B, to define the intervals, and the interval is defined by this formula. Okay, or by this equation. So basically, the bootstrap of the T interval have a second order accuracy. Okay, what it means here is that the coverage error goes to 0 faster than the percentile interval, than the percentile interval as the sample size grow. Okay, but it is computationally expensive because of the nested bootstrap. So within each of the B, we need to run another number of replicates. So it can be, it can also be sensitive to outlier, and in practice, probably the BCA interval would be preferred, because the BCA can also achieve the second order accuracy without having to do this nested bootstrap. Okay, so now we come to our superstar method, which is the bias corrected and accelerated interval. So this is the method that is most recommended in most practical application. Okay, so the BCA interval is actually a modified version of the percentile interval, but it it corrects two things from the percentile interval, which is the bias in the bootstrap distribution, and also the fact that the standard error of the data head can change as a function of the data. Okay, so now let's look at these 2 points. Yeah, number one is the bias correction of Z naught, okay, or Z naught. So this measures the median bias of the data head star. So the Z naught is the inverse normal CDF of the proportions of the bootstrap replicates that are less than the original estimate of the data head. So if the bootstrap distribution is perfectly centered on the data head, and then half of the replicates should be below the data head. In this case, the Z naught would equal to the inverse of phi of 0.5, which is equal to 0. Okay, so in this case, there's no bias correction would be needed. But if more than half of the replicates are below the data head, and then Z naught will be negative, and this will indicate the downward bias. Okay, and also the same, and vice versa for if more than half of the replicates are above the data head. Okay, so the second point is talking about the acceleration, which is A. Okay, so A measures how the standard error of the data head change with respect to the true parameter of the value data. So the acceleration is estimated using the Jackknife replicates of the data head. Okay, so specifically A1, okay, is given by the sum of all the okay, I think A1 here is the adjusted quantile. Yeah, so A1 here is the adjusted quantile alpha 1, So this is a phi of estimated Z0 plus the fractions of these two. Okay, Z0 plus Z of alpha divided by 2 divided by 1 minus some estimated A. Okay, and I believe I may miss the calculation for the A hat here. You can refer this to the book. Yeah. So basically the BCA interval, it reduces the percentile interval when both of the Z0 and A hat are 0, which means that when there's no bias and no acceleration. Okay, but in reality we know that these are very rare to happen. So the BCA will typically give a different and most of the time more accurate intervals than the percentile methods. Okay, so I'm not sure whether we do the I think the exercise for the BCA might be in the book, so you can just refer to the book. Okay, so what is the advantage of the BCA? First is transformation respecting, corrects for scale changes. So just like the percentile interval, the BCA interval is a transformation respecting. So which means that if you apply a monotone transformation to your parameter and then you recompute, so the BCA interval will transform correspondingly. And then the second point says that the second order accuracy, errors in coverage probability go to 0 at the rate 1 over n versus 1 over the square root of n for standard or percentile intervals. So this is the main advantage. Yeah. So we know that the first order accurate methods like the standard normal and the percentile interval would have a coverage error of order 1 over square root of n. So the BCA interval is a second order accurate, which means that the coverage error are of order 1 over n. So they go to 0 much faster as the sample size grow. Yeah. So in practice, this means that the BCA interval will achieve closer to its nominal coverage probability, especially for small and for moderate sample sizes. And the third point here says that they generally consider the gold standard for bootstrap confidence interval. So this is simply the consensus of the statistical literature. So when you are not sure which one you should choose, always choose BCA. Okay, so BCA can be can be obtained by using the function in R, boot.ci. I think maybe later we are going to use the boot.ci. Yeah, we have this one here. Okay, so for the boot of CI, you can have all the 4 options here. You can have a normal, basic, percentile, and also the BCA, and then you can compare. So here is the CI comparisons. Okay, I think you should really run these 2 lines and then see how the confidence interval, which is derived from the 4 methods, are being presented. Okay, so please run this R using the law datasets and then look carefully at the output, and you see that for the I think this one, the statistic is the correlation. It's not the ratio. It's not the ratio, right? Okay, so this is the data here is the correlation. So I want you to run these 2 lines. It's very, very quick and very easy to do this. Okay, so you can see that the correlation coefficient have a moderately skewed sampling distribution. Yeah, and then you can look at the 4 interval types, give a different results. Yeah. So you can see that the BCA interval is more asymmetric, and it does not coincide with the percentile interval. Okay, which may reflect the bias correction in the BCA. Okay, I strongly suggest you to run this. Okay, next we're going to talk about the Jackknife after Bootstrap, like I mentioned before. Yeah, so this is a clever technique that combines the idea from both the Jackknife and the Bootstrap, and it can be used to address a specific practical problem. So now let's talk about the uncertainty of the Bootstrap estimates. Yeah, so a Bootstrap estimate of SE hat of the theta hat is by itself, it is a random variable. So even though it is subtle, but it plays a very important role here. Okay, so when we run the bootstrap and then we compute the estimated standard error, so what we get is a random quantity, and it will depend on which bootstrap sample were drawn. So if we run the bootstrap again and again and again with different random seed, we will get a slightly different value of the estimated standard error. So the bootstrap standard error estimate has its own variability. And then how stable is our estimate of the standard error? So this is quite important for practical questions. So if the standard error estimate varies a lot across the bootstrap runs, which means that it may mean that our inference would be imprecise. Yeah. So we would like to know the variance of the SE hat, which is the uncertainty of estimates. Okay. So the third point says that the Jackknife after Bootstrap can allow us to estimate the variance of the Bootstrap standard error without repeating the entire Bootstrap for each leave one out case. Okay. So here's the challenge. So a naive approach would be to compute a Bootstrap standard error for each of these leave one out sample, which is we remove the observation I from the data and then we run the full Bootstrap and then we get the SE hat of I and then we repeat for each of the I. But this will require n number of full Bootstrap, which can be computationally expensive. Okay. So the Jackknife after Bootstrap method can be more efficient because it reuses the Bootstrap replicates we already computed. Now let us see how this is being done. Okay, so this is the algorithm for the Jackknife after Bootstrap. The first step would be we let J be the indices of the Bootstrap sample that does not contain the ith observation of the X. Okay, so in other words, from our B Bootstrap replicates, we identify which one happened to not including the observation I. Okay, so we do not have to run any new computation. We just look at which row was selected in each of the Bootstrap sample. And then the second step would be there are roughly about e to the minus of 1, okay, which is approximately 37% of the Bootstrap sample that does not contain any given observation in a large Bootstrap. So this one, it follows the probability theory, which says that the probability that a specific observation is not selected in a single draw with replacement is given by 1 minus 1 over n. Okay, and for if we have like n draws, so this will be approximately e to the minus of 1 as n gets large. Yeah, so roughly about 37% of our B Bootstrap replicate may not contain the observation I for each I. Okay, this means that you have a plenty of replicates to work with for each of the Jackknife subsample. So the third step will involve the calculations of the SE hat of B of I using the Bootstrap replicates in J, which is we compute the standard deviations of the detailed hat star of B, okay, for B in J, which is the Bootstrap replicates that exclude the observations of I. And the final step will be to apply the standard Jackknife variance formula to the resulting estimates of the SE hat of B1, the SE hat of B2, and the standard error of B3, and so on. Okay, so this will give you the Jackknife estimates of the variance of the Bootstrap standard error, and then you can assess how stable your Bootstrap analysis is, and it can also help you to identify any influential observations. Okay, so how do we identify this influential observation? By looking at which one, when we remove, it will cause a substantial changes in the standard error estimates. Yeah. So the Bootstrap gives you the replicates, but the Jackknife will give you a way to assess the influence of individual observations on the Bootstrap estimates. So the next slide shows the example in R of the Jackknife after Bootstrap, we use the library boot, and then we just use using the patch data. I think the patch data is the one that we look at the ratio statistics, and then we just run the boot function, and statistic is given by the data underscore boot. I think we have run this before, right? Okay, if you have run this code before, you know that the data boot is actually the ratio statistic of the mean of y over mean of z, if I'm not mistaken. Yeah, and then we run this for 2000 times, and then you can also reduce the diagnostic plot by using the jack after boot. Okay, so and the plot should show that for each observation how much the Bootstrap standard error changes when the observation is being left out. Okay, so the observation with a large influence okay, will be flagged in the plot. So I really want you to run this one, and then to try to understand. Okay, so this plot can also be very useful for diagnostic tool. Okay, so let's say if there is a 1 or 2 observations that drive our standard error to go up, this might serve as a warning sign. Okay, it might mean that those observations are outliers that may inflate the variance estimate, and then we should look at them very carefully. Now let's talk about the cross validation. Yeah, so we turn to the third resampling method. Okay, the similarity between the cross validation with the Jackknife is that in the Jackknife it leave one out. Yeah, and then let's see how similar the idea is in the cross validation. And the cross validation can also be used for the model assessment and also model selection. And cross-validation is one of the most widely used technique in modern statistics and also in machine learning. So the goal of the cross-validation is to assess how the model will predict a new and unseen data. Okay, and therefore it will help us to assess the predictive performance. Now, I think this concept is quite familiar to all of you, especially those who have taken my course on the data analytics. We talked about this in the earlier part of the data analytics. Yeah. So when we talk about the data partitioning in cross validation, so the cross validation is a method to assess the model fit and prediction error. Okay, or it assesses the out of sample prediction error, and to see how well our fitted model predict observations, they were not being used in the process of fitting the model. The second point says that the concept is we split the data into training set to fit the model, and then we use the test set to evaluate the prediction. So this is the fundamental idea of the cross validation. So we train our model on or using the training set, and then we evaluate how well it predicts the test set. Because the test set was not used in the training, so the test set prediction error can be assumed as the honest estimate of the model's true predictive performance. So the third point here is the leave one out CV. Okay, usually we call this as LOOCV, leave one out cross validation. So each observation is used as a test set only once, and then the other n-1 points is used as the training set. So for each of the, let's say you have like n equal to 100, so in the first run you remove number 1, in the second run you remove number 2, in the third run you remove number 3. So this is the most thorough form of cross validation. Okay, so for each observation we fit the model on all the data except just one data, and then we predict the observation on the one that we left out from the sample, and then we record the prediction error for this particular observation, and then we take the average of this prediction error to get our cross validation estimate of the prediction performance. Okay, so as you can see, this leave one out CV is actually directly related to the Jackknife. Now CV for model selection. So I think this is just the algorithm of how to use the CV for model selection. Yeah? Again, for those who took the data analytic class with me, you know how exactly to do this. Yeah. So the algorithm starts with, okay, first the goal is to select between the competing models. So let's say we have model 1, model 2, and so on. Okay. And we have multiple candidate models and we want to choose the one that will generalize best to the new data. So the step 1 says that for each of the model, we compute the average squared prediction error using this using this equation, and then we store it in the CV. So CV is the mean squared prediction error across all of the leave one out predictions. And then the step 2 is that y hat is the predicted value of the x using a model fitted to the data, excluding this one particular observation. And then the third step will be to choose the model with the minimum CV errors. Okay. So among all of the candidate models, we select the one that achieved the smallest cross-validation score, which is the smallest average squared prediction error. So I think this one, unfortunately, it doesn't show until towards the end of the code, but you can refer to the textbook for the full code. I think I should also upload this as a separate additional lecture materials. Yeah, but you can look at this. Maybe I put the font too big. Yeah. So this one is just an example of the CV for the model selection. Probably it is being I'm not sure whether we miss any of this code. Yeah, but you can pause this video and try to run this. So we use the DAG library, and then we use the data iron slide. Okay, so the iron slide dataset contains the measurement of the magnetic iron content and chemical iron content for the rock sample. So we want to compare between the linear model, okay, which is M1 here, and then we have the quadratic model below here. So what we do is that first is we compute the error based on the linear model, but the error for the quadratic model we cannot see here. Okay, so and then from there we compare the mean of the first model and the mean of the second model, and we find that the quadratic model has a lower prediction error. Now the part where we do the leave one out is this one. Okay, so y is equal to the magnetic of negative A and x is equal to the chemical of negative K. And then this is a loop function, even though it doesn't show all of the function. So I want you to refer back to the book, okay? Because this one, for each of this, for each of the replications, we remove one observation. Okay, now let's talk about the summary and what is the best practice. Again, Bootstrap is more general and handles non-smooth statistic better than Jackknife. Okay, we already saw this when we discussed the failure of the Jackknife, especially for the median. Yeah, and the second point says that the Jackknife is faster for smooth statistics because it only requires an iteration. So if you have smooth statistics like the means, correlation, regression, okay, probably you want to use a Jackknife, which produce a deterministic result with exactly the same number of evaluations as your sample. Okay, so if you want to run Bootstrap for smooth statistic, you probably need to run it for like 1,000 or hundreds of evaluations. Okay. So the third point is the confidence intervals. We see that the percentile and the BCA, mostly BCA, are more superior to the normal interval, especially when the data is skewed. Yeah. So we need to know and that the standard normal interval would assume normality of the data hat. But if the distribution is skewed, okay, which is very common for statistic, for example, like correlation, variance, and ratio, and in this case, we cannot use the normal interval. Okay, so the percentile and also the BCA, it does not make any normality assumption, and it can automatically adapt to the shape of the Bootstrap distribution. Okay, but most of the time BCA is preferred over percentile because of its advantage of correcting the bias by using the second order accuracy. And the nested bootstrap, if we want to use the bootstrap T, we need to have a nested bootstrap, okay, which make it computationally expensive. Okay, so the bootstrap T, the advantage of using this is it has an excellent theoretical property, but it can be very, very computationally intensive. Yeah. Okay, so the best practice is always use the boot package in R for efficiency. And then when we estimate the bias, ensure that the statistic is smooth. Okay, and for BCA interval, whenever possible, as they are use BCA interval whenever possible, as they are transformation respecting and accurate. And we use the Jackknife after Bootstrap to check the influence of the outliers on our Bootstrap estimate. So we check the variance of the variance. Yeah. And this is some of the guidance on the sample size and the replicates. Okay, so you can refer to this, and this is just a final thought. Yeah. So resampling is a powerful tool when the theory fails. So this, I think, is the key message of this whole lecture. So when you face a situation where the classical distribution of the assumptions is you have a suspicion on the classical distribution of the of the assumptions of the classical distribution, okay, or when your sample is small, or when your statistic is complicated, and then we can use this resampling method to give us the solution. So we do not have to know about the sampling distribution analytically. We just have to run it empirically using the computer. Okay, but the resampling method is also not a magic. Okay, so if the sample is not representative of the population, even with resampling will not help. Yeah. And then the bootstrap is a way to pull yourself up by your own bootstrap, but you still need boots. Okay, so what it means here is that the idea here is that it captures both the power and the limitations of the methods. Yeah. So the boots are your data. So you need to have a good data to begin with. But even with the good data, the bootstrap will allow you to do inference in situations where traditional methods cannot. Yeah. So I think that's all for today's lecture. Thank you, and I hope you find it clear and engaging. And then we'll meet again for our last class next week. Goodbye, everyone.